I'll begin. Dear Heavenly Father, we thank you for this day. We thank you for the weekend. It's about to start. And just pray you'd just bless this class, Lord. In your name I pray. Amen. You might as well turn in your homework. You've spent enough time on the last 5 problems. If it hasn't happened already, it's probably not going to happen in the next 30 seconds. Thank you, sir. Thank you. Thank you very much. So today we are talking about calculus. So today I want to talk to you guys about the, calculus with linear algebra. Worlds are about to collide. All right, so, we have done token examples that involve differentiation of polynomials and things like that, right? But I want to show you a non-trivial application of what we've done in terms of linear algebra to calculus, all right? So the basic theorem we need from calculus to get us started is the multivariate Taylor's theorem. So let's let f be a function from, let's say, Rn to, I've lost my place. To R. All right. So think about a function, an n-variate function with n inputs and 1 output, a real valued function of n variables. Be nice. Then, and by nice, what I really mean is real analytic, meaning that it has a power series and the power series approximates the function near the point in question. We can expand f of x equal to, well, the sum I equals 0 to infinity, n equals 0 to infinity. All right, of the sum I sub 1 comma comma I sub n. I'm sorry, I shouldn't use n here. N has a fixed but other has a different meaning. I need to use some other index other than, see, n is the dimension here, and this shouldn't be n. So let's use k here, okay? I1 through ik, and these indices range from 1 to n. All right. And then you got your 1 over n factorial here. K factorial. And then the kth derivative of f with respect to partial xi1, partial xi2, partial xik. You evaluate this thing at, let's say, the point. Let's use a for the point. All right. And I should, I should tell you the rest of the preamble to this, and the rest is not much to say. But then, for x near a, I have this. I'm not done yet. So what I just wrote down, these are numbers. All right. And then you multiply these by x sub I1 minus a sub I1, x sub I2 minus a sub I2, x sub ik minus a sub I k, like that. This is the multivariate Taylor expansion. You can derive this by plugging in a parameterized curve into I mean, you can look at the function f evaluated with a path, a linear path of one variable. That will give you a function just of a real variable from a real variable. You can apply the ordinary Taylor's theorem to that, and when you do that and combine it with the chain rule in Calculus 3, this pops out. But that's not something we should do in here, because that's really not this course. This is a known result, is my point. Now, I actually don't even care about all this. I'm just going to focus our attention on the start of this. So the first three terms, actually, k equals 0. What we understand all of this. What does this become when k equals to 0? By definition, that notation, what it's meant to mean when k equals to 0, what's the 0th derivative? The function, right? So we have f of a. That's the k equals 0 piece. Then we have plus the sum I equals 1 to n of partial f partial x sub I at a times x sub I minus a sub I. That's k equals 1. K equals 2 in this thing is the sum I and j equals 1 to n, partial squared f, partial xi, partial xj, evaluated at a, times xi minus ai times xj minus aj. So there you go. That's what k equals 0 looks like. K equals 1, k equals 2. These are the 0th order, the 1st order, and the 2nd order pieces in the multivariate power series expansion to a function of n variables. Do you remember this from Calculus 3? Probably not, because American calculus books think you're stupid, and they refuse to expound these things clearly, which is sad, really sad, honestly. You spend a lot of money for those books. This should be in there. But anyway, this you do learn in a different notation. This is what? This is the gradient of f at the point dotted with x minus a. This you certainly learn. What I've written so far, this is the linearization of the function. Right? For a function of two variables, if you set z equals to this thing, that's the graph of the tangent plane. And then what is this? Well, we can rewrite that as q at the point A evaluated at, well, x minus a. Plus dot, 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 dot. Where this q is a mapping from Rn across Rn to R. Sometimes this is called the Hessian. Usually its matrix is what's called the Hessian, though. All right? So just for those of you who've had Calculus 3, let me just demystify this a bit. For n equals to 2, we can look at z equals to f of xy as a graph, right? That's some kind of curvy graph, right? So then if you look at z equals to f of ab plus fx at ab times x minus a plus fy at ab times y minus b, right? This is the what? This is the equation of the tangent plane to the point a comma b comma f of ab. So if you just take the first three terms in what I wrote, and you set that equal to the, if you're looking at the graph of a function, of n variables, then the graph of the first two terms is the linearization of the function. You know, the graph of that would be what I would call the tangent plane, or perhaps tangent hyperplane, depending on how many variables you got. This you did do in Calculus 3, right? You did. But this next piece over here, probably not so much. So what does that quadratic piece look like? So specifically, Q, you know, Q. What is? So I'm going to drop. We'll drop the A, or maybe I guess we could write Q sub. I don't know. Q is a mapping from Rn cross Rn to R again, right? And so essentially the formula for it is this: Q of x is equal to the sum I and j of partial squared f partial xi partial xj. Oh, I should use something other than x here. You guys pick, let's say h. So hi, hj, right? You could rewrite this as like the h vector times the matrix of Q times h again, right? Excuse me, not h, but what? H transpose. I mean, this is a quadratic form, is my point to you. What's the ijth component of the matrix for this quadratic form? If you want to get fussy, I should really be doing all of this at a specific point. So I dropped the a. I mean, you probably should say Q of a. The partial derivatives are being evaluated at the point a. It's all at a. A. What can you tell me about partial derivatives? What did we learn? One of the things you learn in calculus but never prove is that you can commute these. That's something I should have proved in advanced calculus last time I taught it. But I didn't, because I'm lazy. All right. But I should be less lazy. All right. You could disagree with that. Anyway, Qji is equal to Qij, which is to say that the matrix of Q is symmetric. What's that mean? That means the real spectral theorem applies. Right? So if I call this thing, you know, if I call this, say, the matrix of Q, if I give it a name, say, call it A, then this has A equals to A transpose, right? Which implies that we can rewrite Q of H as something like lambda 1 H bar 1 squared plus lambda 2 H bar 2 squared plus lambda, you know, however many eigenvalues you got, let's say n, H bar n squared, right? It says we can choose a system of eigencoordinates which diagonalizes the quadratic form, and that's the formula for the Hessian with respect to that system of coordinates. This is the application of the real spectral theorem to this quadratic form. What's its significance? Right? Well, let me get my head out of the clouds for a little bit here and do an example or two. We'll come back to what that means for us, okay? So let's do an example. We'll get back to this. So if I had f of xy equal to, you know, I don't know, x e to the y squared, say, right? Then we can calculate what's partial f partial x equal to. What's partial f partial y equal to? So the way partial differentiation works is we just differentiate x holding y fixed, so this is just e to the y squared. And this one treats x as a constant, so we get x times partial y of e to the y squared, and then the y partial derivative is just like an ordinary derivative for those of you guys who have not had Calc 3. Trust me, you can learn this with far less effort, for example, than it took you to learn elementary row operations. Elementary row operations are like way harder than partial differentiation, as an example. Those of you who've had Calc 3, do you agree? Yeah, okay. Anyway, here we go. So this is 2xy e to the y squared by the chain rule, right? And then we can calculate second partial derivatives. See here, partial squared f partial x squared is what? And what's partial squared f partial x partial y? And what's partial squared f partial y squared equal to here? First one's easy. Yeah, 0. And the second one? You can either differentiate this one with respect to x or that one with respect to y. Either way, you get 2y e to the y squared. You notice that? That's that symmetry I was just talking about. If you take this and differentiate with respect to y, or if you take that and differentiate with respect to x, either way you produce partial squared f, partial x, partial y. So the order of partial differentiation commutes for nice functions, and this is a nice function. And then the second y derivative is what? Oh, that one hurts a little bit. So that's really 2x partial y of y e to the y squared, right? So partial squared f partial y squared is 2x times what? Well, times 2y squared e to the y squared plus e to the y squared. All right, so anyway, my point is I've calculated all of the partial derivatives up to second order. I have everything I need now to construct an approximation of this function at a point. Let's see here. Does this function have a critical point? Do you guys remember what that is? What's a critical point? A comma b is critical point if this thing called nabla f of a comma b, which by the way is fx evaluated at ab, comma fy evaluated at ab, if that is 0, right? So for those of you who have not had Calculus 3, I just cavalierly used some common notation you may not be aware of. Sorry about that. But this is notation that people typically use. F sub x is equal to partial xf is equal to partial f partial x. Okay, that's pretty much it. But these are 3 common notations for partial differentiation. So does this function have a critical point anywhere? It does not, because the x derivative is e to the y squared, which is never 0. So this function has no critical points. That said, we can expand the function about any point we like. So you guys pick any point you like. A comma b equal to what? You pick my point for me. 711. 711. That's interesting. All right, so that we have f of xy is equal to f of 711 plus the gradient of f evaluated at 711 dot product with x minus 7, y minus 11, and then plus another piece. All right, so let's see here. That is equal to, we plug in 7 and 11. So we've got 7 e to the 121 power. Nice. And then plus the dot product of e to the 121. Give me a arithmetic workout, huh? And then 2 times 7 times 11. Fun. So 7 times 22. 144? No, it's not right. What? 154. Okay, 154 e to the 121. This is why I shouldn't give you guys the choice to pick numbers. Let's see here. So you could take the dot product there. You know how to do that, right? And then what's the other term? The other term is plus, you take x minus 7 times a 2 by 2 matrix. And the, oh, I'm sorry, not just x, it's a row vector. So it should be the row vector x minus 7, comma, y minus 11. And then over here, we do x minus 7 times y minus 11. What goes in this box? That's the matrix of Q. So like, I'll do it over here symbolically. The matrix of Q in the two-dimensional case looks like fxx, fxy, fxy, fyy. That's the n equals 2 Hessian right there. So we just need to evaluate those second derivatives at 7-11, thanks to you guys. Let's see here. Actually, mostly just Nathan, right? This is all Nathan's fault, is it not? Let's see here. Oh, wait a minute. Liam threw his voice. Nice work. Unfortunately, the rest of the class is not your friend. So, as they ratted you out just now. Let's see here. So, 0. I do that one. I got 0. I pinned that down. 22 e to the 121. 22 e to the 1. I do not recommend a decimal approximation for this. I don't know if you've ever calculated e to the 121, but I assure you it's large. I mean, it's about 3 squared to the 60th, so it's something like 10 to the 50th. Anyway, guesstimating. Oh, and then the other one. Yuck, this thing. So when I plug in this, I get 2 times 7 plus, times parentheses, 242 plus 1 e to the 121. Okay, so it's harmless enough. It's just 14 times 243 times e to the 121. All right, so there you go. That's the best. That's the best quadratic. That is the best quadratic approximation to the function x e to the y squared, centered at 7-11. So what that means, guys, is that if you were to think about the graph of z equals to x e to the y squared, right? That would be some kind of, I don't know what it looks like, whatever. All my graphs kind of look the same. But it would look something like this, yeah? And so you can understand what we're doing geometrically. So, of course, the stupidest thing is the first term in the expansion, which is just the base point, right? So you put z equals to, let's say this is the 7, okay, fine, I'll pretend, 7, 11. So it's something like here, obviously, right? So if you just put z, obviously not to scale, if you put z equal to 7, once I write the formula, you'll see why it's not to scale. 7 times e to the 121. So that's how far we're up here, like right here. 7 times e to the 121. Then this would just be a flat horizontal plane. That's the first and most stupid approximation to the graph. Just a constant horizontal plane, right? Then we can do a little bit better when we add the next two terms, right? Z equals to I'm just going to write it symbolically, f of ab plus the, fine. I'm sorry, I'm not going to write it again. This stuff right here, star. Z equal to star. This is the tangent plane. Well, the solution set to that is the tangent plane through that point, right? Then if we also include the Hessian, what we've got is some sort of like, you know, some sort of, you know, like curve. So I'm saying everything all the way up to everything. Call that star star. The whole thing, that's the best quadratic approximation. And what does that look like? What does that actually look like? Well, that depends on this matrix, actually, right? But it's a straightforward but tedious task to show that there exists a system of coordinates where we can rewrite that matrix in what form? I mean, you could rewrite star star as well, the constant term, the linear term, but then over here you could of course rewrite that quadratic piece in terms of lambda 1, you know, h1 bar squared plus lambda 2 h bar 2 squared. So like this piece right here, we can use the real spectral theorem on, right? And that will kind of reveal what it looks like. So if both of the eigenvalues are positive, well, it's hard to say because the presence of the non-trivial presence of the linear term is cramping my style. Like if this is gone, if this middle term is gone, it's really easy to say what this is as a graph. All right, let me back off this complicated example and try to do something more simple. By the way, you can pretty much do the same thing. Oh, yeah. Oh, this survived. Okay, that's good. I just found them again, you know. I can't do min-max or anything interesting much if I put an m here, but it's pretty easy for this. There's a similar theorem if you want to approximate a function going from Rn to Rm for x near a. Then the theorem says f of x is equal to, well, f of a. And then the interesting thing, what comes next, is the Jacobian of f at a times x minus a. All right. And then higher order stuff that I don't care about. What's the Jacobian of f? Here, this Jacobian of f at a. Well, I won't write it out. I'll just write it generically. It's partial f partial x1, partial f partial x2, partial f partial xn. So this is how you find the best linear approximation to a function that has a vector input and a vector output. You just use a matrix of partial derivatives, and that gives you the linearization for the function. And for if you're near the point that we're expanding about, if you're near the point A, it's a very good approximation. The things that are in the plus dot 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 are smaller if you're close to the point of tangency. Okay, anyway, this I explain in more detail in advanced calculus, so you can join me there if you want. But what I want to do here is focus our attention on the case where we do have a critical point. Because when we have a critical point, this gets simpler. Right? Critical point is when we have the gradient 0. So what happens if we've got a function of two variables, right? Function of two variables. suppose we have, f going from R2 to R, a function of two variables, and we're at a point such that at the point AB we get 0. So it's a critical point. At such a point, what does the multivariate power series expansion look like? We have f of x comma y equal to, well, f of a comma b, right? Plus what? Plus something that looks like x minus a, y minus b. We've got this 2 by 2 matrix, right? fxx, fxy, fxy, fyy. And I'm just going to say the whole thing at the point a comma b because I'm tired of writing a comma b everywhere, but it's there. I mean, we have to evaluate at the point, the critical point, this matrix. And then times the column vector, x minus a, y minus b. But this is a symmetric real matrix, right? So there exists some kind of similarity transformation we can do that diagonalizes it, right? We can choose eigencoordinates. And with respect to that system of eigencoordinates, we can rewrite this as what? Something like, lambda 1, let's say delta x bar squared plus lambda 2, delta y bar squared. Well, I'm sorry, I'm an idiot. Why don't I just say x bar and y bar squared and stop being a doofus? Let's see here. Lambda 1 technical term. x1, lambda 1 x bar squared plus lambda 2 y bar squared. This is easiest to think about when a and b are both 0, right? So for example, a equals b equals 0. We could consider f of xy equal to 2xy. F of xy equal to 2xy, that has, f of 0, 0 equal to 0. It has the gradient of f being 2y comma 2x, right? Thus, the gradient of f at 0, 0 is 0. 0 is a critical point. And so so we have, what's q? Q of xy would be equal to x comma y, the matrix 0, 1, 1, 0, xy. I showed in the help session yesterday how to diagonalize this matrix. I showed how to choose a system of coordinates x bar and y bar that puts this matrix into a diagonal form. We derived that this is equal to, actually I forgot now. Somebody have their notes from yesterday? I mean, I remember the eigenvalues, I don't remember the other stuff. So you guys will help me out here. This has eigenvalues, what? Lambda 1 equal to? Which one did we make the minus one? The first one was minus 1. Lambda 2 was 1. And what was the formula for x? For x, x was equal to what? No, but what was the formula for x in terms of x bar and y bar? No, I'm talking about the formula for x. 1 over square root of 2. Yeah. X bar minus y bar. And what was y equal to? 1 over the square root of 2.
X minus y bar. Oh, the other one's negative x.
Negative x bar. And this one is what? X bar minus y bar? Okay, so if you take what you can derive this. I showed how explicitly in the help session yesterday to derive that for this matrix. Calculate the characteristic equation. You find eigenvalues plus or minus 1. You explicitly can work out the change of coordinates to the eigencoordinates like right here. When you plug these coordinate change formulas into 2xy, what pops out is minus x bar squared plus y bar squared. Right? So what does this tell you about the graph 2x? If I look at z equals to 2xy, what's it look like? What was the eigen, what was the, oh, is this the one where I let you pick it, Bethany? It's all your fault. So it was -1, wasn't it? Oh, see, now that really hurt. This was u1. That's supposed to be in the xy plane. Ah! That's in the xy plane. Believe it. Yeah. It's in the xy plane. I know it doesn't look like it, but imagine that u1 is in the xy plane, and then that's eigenvector with eigenvalue -1. u2 is what? It's perpendicular to that I remember. What was it?
U1 was -1, and then U2.
-1, 1, okay. And u2 was minus. Oh, so it's actually over here. This is u1. And u2 was what? -1, -1. So this is, all right, so I know it's kind of hard to believe, but this is a right angle, and both of these vectors are lying tangent to the xy plane. Use your imagination. Or figure out how to draw a better picture than I can. Good luck to you. The larger point, though, is so this is where the y-bar coordinate system goes. This is where x-bar goes. And that formula, if I put z equals to this, right? If you put x-bar equals to 0, what happens? X-bar equal to 0, you've got z equals to y-bar squared, right? So it grows like a parabola along the x-bar equals to 0 slice. And what happens to the other one? What happens when you look at z equals to, put y-bar equal to 0, what happens? If you put y-bar equal to 0, if we put y-bar equal to 0, we get z equals to minus x-bar squared, right? So in other words, along the other, along the x-bar, we grow down like that. So it's easier for me to illustrate with my hands. We're talking about a surface that along the y-bar coordinate axis it's going up like this, right? But then along the x-bar coordinate axis it's going down like that. That's what's called a saddle. So this is a saddle shaped, and I can see that from the fact that the eigenvalues are -1 and 1. So all I'm trying to tell you guys here is that we can tell at a critical point the nature of the critical point pretty easily by just direct geometric reasoning on the eigencoordinates, right? If you think about it, just look at this formula, right? It says that if lambda1 and lambda2 are both positive, basically we're looking at something that looks like z equals to f of ab plus lambda1 x bar squared plus lambda2 y bar squared, right? What's that say about this? For this case, this means that we're what? F of ab is a what? What if we had lambda1, lambda2 less than 0? Then f of ab would be a local what? If they're both positive, it's a minimum, right? Because any which way you go away from the critical point, you're raising the value for the function, right? You're adding a sum of squares. It's getting bigger. So if they're both positive, it's a local minimum. If they're both negative, it's a local maximum. And if you have the product of them, lambda 1, lambda 2 is negative, then f of AB is at a saddle point. Now, if either of the eigenvalues are 0, we can't say anything, because then the third order piece in the power series approximation becomes dominant, possibly. Or maybe it's trivial, in which case you have to look at the fourth order piece and so forth. You may or may not recall this, but the second derivative test from calculus 1, it fails when the second derivative stuff is 0, right? You actually have to keep going up the power series approximation to find the first non-trivial term to analyze whether you've got min or max. Think about it. So, by the way, guys, this thing I just said, does it really matter that we have 2 variables? If we had 3, 4, 5, 6, 7 variables, the same comments would be true. If all of the eigenvalues are positive, it's at a minimum. If all of the eigenvalues are negative, it's at a maximum. If you have a mixture of positive and negative eigenvalues, you're at a saddle point, even though I can no longer graph a function of more than 2 variables. Like, what does W look like? W equals to f of x, y, z. Can you picture it? I can't picture it. I mean, I can look at level surfaces. I can look at x plus y plus z equal to 1. That's a plane. Or x squared plus y squared plus z squared equal to 1. That's a sphere. I can look at level surfaces, but I can't look at graphs of 3 variables. OK, great. What do the eigenvalues have to do with this 2 by 2 matrix is the thing, right? So our 2 by 2 matrix, fxx, fxy, fxy, fyy, what are the eigenvalues of a 2 by 2 matrix? Fun facts. The trace of A is the sum of the eigenvalues, right? What's the determinant of A? Product of the eigenvalues. Hey, look at these 2 top cases. Did you notice something? These 2 top cases, they have the product of the eigenvalues. It's positive, don't they? So you can group the min-max case into one case. That's when the product of the eigenvalues is positive. It's either plus plus or minus minus, but anyway, the product of the eigenvalues is positive. And so what tells us about that? Well, the determinant. What is the determinant of the Hessian? It is fxx, fyy, minus fxy squared. Or big D, as it's known in Calculus 3 in a lot of books. This is where that mystical theorem comes from. You're looking at eigencoordinates for the Hessian. Looking at the determinant of this tells you the product of the eigenvalues. I personally think that's neat, but anyway. Does that make sense? I mean, so whether this is positive, if it's positive, we're in the min-max case. If it's negative, we're in the saddle case. So positive, this quantity at the critical point gives us a min or max. Negative, this quantity at a critical point gives us a saddle. If this is 0, then we can't judge min or max looking at the Hessian, because the power series may be non-trivial higher up, and that matters. The things I haven't written beyond here, there is a plus dot dot dot. It's third or fourth or fifth order, which is even smaller close to the critical point. So since we're looking at local min or max, it doesn't matter. All right, so there's one other important, well, there's one other, listen to me. There are so many places where linear algebra helps you understand everything with more depth. But certainly calculus is a good place. I mean, differential equations is the other place I have a lot more to say about. But I think I'm just going to take the last 5 minutes of class rather than diving into DiffEq, which we could do, but I'll probably spend all of Monday talking about that and your questions. The story of differential equations and how we solve differential equations with eigenvectors and generalized eigenvectors, that brings us back to talking about eigenvectors and generalized eigenvectors, which would serve you well for test 3, right? So the last new material we're covering, I think, as far as I can think of, is pretty much just how we solve systems of differential equations with eigenvectors and generalized eigenvectors and the Jordan form or the real Jordan form, all that fun stuff. But here's one of the things we're supposed to talk about in this course, which is the problem of geometric linear programming. Do you guys know what that is? The problem is this. You've got an objective function, which is, say, f of xy. You've got a constraint, or often called feasibility region. And the feasibility region is something like this. It's typically some sort of region in the plane, all right, bounded by a set of linear inequalities. So a typical point in here it solves a set of linear inequalities. There's a theorem of analysis or topology, depending on your viewpoint, which says that if you have a continuous function and you feed a continuous function values from what's called a compact set, you attain both a minimum and maximum. So this is a theorem. F of compact is compact. This is continuous. So if we're talking about f from R2 to R, what's a compact set? A compact set of real numbers is just a closed interval. And a closed interval has a biggest and smallest number in it. So the first place you see this theorem is the extreme value theorem in Calculus 1. Continuous image on a closed set, it attains a min and a max, right? Anyway, so the objective function here, I haven't told you yet, the objective function has the form ax plus by plus c. This objective function comes from like setting inventory at a store or something. It's some sort of linear combination of variables. All right? A, B, C are constants. What's the gradient of f? A, B. That's it. That's the gradient of f in this case. Are there any critical points for a linear objective function? Not unless A or B are both 0, right? And if A and B are both 0, that's not the kind of problem we're talking about. So this is not equal to 0, right? Therefore, no, local min-max to be found in the interior of the feasibility region, which I should give a name. Seems like Pac-Man is a good name. All right. So I'm saying this set right here is Pac-Man. All right. So where do the min-maxes have to happen? They have to happen on the boundary of Pac-Man, on the edge. But here's the thing. When you get into that, right, if you restrict this function to the edge, you're still looking at a linear function on a compact set. And if you calculate the gradient, if you calculate the derivative of the function restricted to the edges, you'll find that those are also non-zero. Which leaves you what? What are the possible places where you could have min-maxes? They're the places, the corners, right? The places that are neither interior to the edge nor to the interior of the interior, like the genuine interior. And that's geometric linear programming in a nutshell. It says when you have this problem, it suffices to look at the vertices of the feasibility region, and that will tell you where you have mins and maxes. This is easily derived from min-max theory in Calc 3. Did you prove that in your Calc 3? I didn't. I haven't proved it yet this semester in Calc 3 either, so there you go. Actually, I did. I talked about it in Calc 3 this semester, and what I discovered was something horrifying, which is that 80 to 90% of students have not seen geometric linear programming in high school. For shame. This is a pretty simple topic that is actually very, very relevant to a multiple of jobs I don't care about having. That's the start of linear programming, which is, optimization you would use in like scheduling stuff for a business. It's an important math skill for everybody to have, really. Anyway, I digress. Have a good weekend, you guys. Just think of it. The previous mission is over. There's one more to go.